Hello, everybody, and welcome to Michael, aka Cable Thief, and Dominic, aka Singe's wireless hacking village talk at DEF CON 29. We're going to be talking about how to efficiently recover the NT hash from an MS Chat version 2 exchange. Michael and I are both penetration testers at Orange Cyber Defense's SensePost team, and we both have an interest in hacking Wi Fi. Mine started in 2014 with the release of the Mana Toolkit, and Michael started a little bit before 2016, where he released WPA Sycophant Peep Relay attacks at DEF CON. But today we're talking about something completely different. Assless Chaps, and why MS Chap version 2 doesn't adequately protect its ass, and how we can use that to more efficiently attack it than engaging in a DES brute force. The structure of today's talk is Michael's going to open it up with a brief eulogy for MS Chat version 2, more specifically about how it works and why we don't actually need the cleartext password, but we can just use the NT hash to crack it, and why that's useful after the fact. He's then going to talk about some hashcat modes that he developed to crack that using hash lists rather than word lists. I'm then going to take over to go into a little more detail around the DES crypto of MS Chat version 2 and how others have done it in the past, how they've made DES brute forcing more efficient, and how we can escape that trap by using a database lookup instead on a hash list, which gives us really efficient NT-hash recovery of MS Chat version 2 challenge responses. We're then going to talk about a tool we're releasing today called Assless Chaps and some related hashcat tooling for generating your own word lists. So enough with the agenda. Let's move on to the talk. MS Chat version 2 has been declared dead longer than I've been in the industry. In 2003, Joshua Wright declared MS Chat dead when he developed Asleep and showed some of the early cryptanalysis against it. In 2012, it was declared dead after Moxie Marlinspike and Dave Van Hulten's DEF CON talk, and it still somehow seems to be around. Part of that reason is the people who keep declaring it dead are the hackers, but the people who keep using it are the industry. So we're hoping that this talk puts the final nail in the most frequently used authentication protocol on corporate Wi-Fi and a fairly frequent protocol used on PPTP VPNs. But before we put it in the ground, Michael's going to give it a brief eulogy by explaining how it works. Over to you, Michael.
Right. Thank you, Dominic. Right. So before we go into what we find objectionable about MS Chap, we need to understand what it's for. And the idea behind MS Chap is that we can prove knowledge of a secret without transferring that secret directly. So, and as well as the authentication is mutual in that we're going to be authenticating against something, and that something needs to show us that it also knows the secret. So this is the whole point. So you go around with your Wi-Fi device, you're not necessarily trusting everything. You don't want to just give away your password all the time. So instead you do this little song and dance. So let's go through the song and dance. We're going to use here a example of King Arthur, King of the Britons, communicating with a Frenchman, asking to come into a castle to look for a holy grail. So Arthur approaches the castle. He announces, "Hail, I'm Arthur, King of the Britons." After which the Frenchman challenges him, sort of, "Who are you? What do you want?" etc. In the MS Chat world, this is going to be a 16-byte random bit of data that gets thrown at Arthur as a challenge. Arthur takes that 16 bytes. He generates his own random 16 bytes. He then takes those two things, puts them together, and then with his password generates an NT response. So the randomness that went into this is the two challenges, his password, and that sort of gets him this NT response, which he throws back at the Frenchman. The Frenchman then has enough information to redo the same calculations Arthur did, and he can then compare it to the response that Arthur gave him to make sure if he puts in all the same inputs, including the password that he's aware of, whether he gets the same outcome. And if he does, he knows that Arthur knows the password. So then what does he do? He takes all the sort of randomness that has occurred until now, does his own things with his version of the password that he has, and he throws it back at Arthur as an authenticator response. This is if it's a success. So he prepends an S equals and then that random bit of data. This way, Arthur can see, okay, cool, this guy's sent me back a authenticator response. If he repeats all the same actions, he should get the same authenticator response, thereby proving that the Frenchman knows the same password he does. What's more likely to happen in this particular interaction is that the Frenchman is going to reject him and not send him back an authenticator response, and instead send back a live cow towards Arthur in retaliation to tell him to get away. Right, so now that we know what it's for in the general outline of it, let's have a closer look at those different operations that they each do. So the first thing we're going to be interested in, let's dive deeper is what I should say. So the first thing we're going to do is we're going to look at how those two random bits of 16 bytes get put together to generate the 8-byte challenge that we're expecting. And when you are doing MS Chap cracking, this is the challenge you're going to see. So the first thing we do is we take the username. In the interaction we just saw, it would actually be Arthur, King of the Britons, or Arthur Pendragon. We take the authenticator challenge, so this is the random bit of information the Frenchman threw at him. We take Arthur's random bit of information. We SHA all of these together, and then from that SHA, we only take 8 bytes off of it, which then is the challenge that is used in further calculations. So the reason I'm going through this first is I don't want to sort of muddy up the slides with a bunch of unnecessary things. So that's how we get the challenge. With that challenge, we generate the NT response. So what we do, we take the password, we MD5 sum it, which gets us the NT hash. With that empty hash, we add in the challenge. We do some des magic to this, which Dominic will go into a bit further. And this gets us the NT response. From the authenticator side, so this is the Frenchman now proving to Arthur that he also knows the password. We take the password, we make it an NT hash, we hash it again for reasons. We take all the other random bits of information, so the username, some random static bytes. So they're just in the RFC, so everybody knows them. The challenge that we calculated 2 slides ago, and then that gets us the NT response. Oh, and we add in the NT response, and we SHA it. We prepend an S, and we throw that at Arthur. And you can see in this way, we know what gets put into this is the password, and if we both know the same password, we should both be able to repeat these same actions to get the same result. The thing is, we don't necessarily have to know the same password. If we look a bit closer, we actually just need to know the same NT hash. Right? So here we have the NT response, where if we were to just skip the password stage and immediately go to the NT hash stage, we would be able to generate the exact same response. And the same from the authenticator side, where if we just knew the NT hash, we could then immediately go into the rest of it, thereby bypassing everything. So this makes a lot of sense, as otherwise Windows domains and things would be having big lists of just straight up usernames and passwords. And obviously, they don't have that. Instead, they have a big list of NT hashes. And so NT hashes are kind of built into the system, and therefore we can kind of pass the hash. So my idea behind this was, if I have a big list of NT hashes, wouldn't it be nice to set up an evil twin and then pass the hash to people, right? So where I don't need to crack everything. Instead, I just have a big list of hashes. Say if I'm on an engagement and I've compromised the Active Directory, and then I want to do some man-in-the-middle attacks against users and they're using PEEP, I can then just plonk those straight into my rogue, and therefore I can return valid responses to people. Luckily for me, I went looking. Host APD and WPA supplicant support this. So you can see here I have 2 examples of configs. The network one in WPA supplicant, you essentially say password equals hash, and then you give the hash. And then for the server side, so the access point side, once again, instead of a password, you just prepend hash, and then you give it the hash. So this is amazing. So in essence, built into the protocol, essentially, you can pass the hash to get onto Wi-Fi and things like that. So this is very nice. What this also means is we can use things like hash lists instead of word lists to crack these things, because essentially what you're doing when you're recreating this action is you're just skipping the first step of turning it into an empty hash. Instead, you're just plugging in the empty hash directly. So when you crack against words, you're generating rules and all sorts of things. And since it's sort of naturally salted, it can take quite a while, etc., etc. So my idea was we get sort of hash sources like domain Active Directory sources, or more specifically, the one that interests me was the Have I Been Pwned database, where Troy Hunt, who runs an amazing service, provides a way to download a bunch of NT hashes. So these NT hashes are going to be from dumps that Troy has collected over the years, and then he provides that to people to make sure their users aren't using previously compromised passwords. This makes a really nice, up-to-date database of a bunch of dumps and sort of user passwords that you might not necessarily have access to, because most of them, a lot of them at least, are given to Troy in confidence. So this gives us a lot of information. And the other nice thing, what people usually do with these dumps is they then crack them to generate the word lists that we then use and apply rules to, etc., etc., etc. Some of these are never going to be cracked because the password is maybe just too good. So in that instance, if we use the hash list directly, we don't even need to go through the bother of cracking these things. We're just using it directly. What you do miss out on, though, is the ability to add rules to these things and sort of mutate them in fun and interesting ways. But Dominic's going to go over some things around that later. So now that I had a source of hashes, I wanted to be able to verify that the hash I had matched the challenge response I was seeing. So I went looking around again, and I found some hashcat forum posts, one by Atom and one by EvilMog, based on Atoms, where Atom was giving an interesting example of using the new DES cracking mode to reverse or brute force the DES on a MS chap or NTLMV1 challenge response, right? So what he was doing was he was breaking the challenge response into three, doing a bunch of cryptographic actions on it, and then brute forcing the entire DES key space, which is, I thought, this is brilliant. I don't even need to use these hash lists. Instead, what I can do rather is just brute force the entire key space, and then you're guaranteed to get the hash, not that it's maybe an existing one in this hash list you found. So I got this all set up on my laptop, ready to go, keeping in mind my laptop is quite a small, dinky MacBook. Started it up, and it promptly told me it was going to take me 4 years to do the entire key space. So that's when I decided to go back to hash lists. And then looking at EvilMog's post, he went through the process to get to the brute forcing stage a little bit more clearly, I felt. And so I followed that process. It did require me to sort of finagle things a lot. Given that I wasn't just brute forcing and providing a mask, I had to take my hash list, sort of chop it into pieces, and then apply things. And it was just a lot of work. So I thought, what would be better than this would be if I just created a module for hashcat. So I felt this would be really simple, given that we have an existing module for MS or NTLMV1, which essentially just includes an extra MD4. So all I should be able to do is copy that and just delete one line, and I'm done. So that is what I did. And I created two new modules, 27,000, 27,100. Someone else I'd like to point out here is I did this I submitted this idea to a hackathon internally, and I got a team, and I'd like to thank the team for that as well. But yeah, let's give an example of these hash modes working. So, right. So I'm just going to use a example hash and then an example hash list filled with NT hashes. We're going to run that. We've just got pot file disabled so that we don't re-crack something that we have already gotten, because obviously we've been testing with this a little bit. And off we go. Cool. And we get test out. And if you see at the end here, the password that it outputs is a NT hash. Brilliant. So now, given that I am skipping an entire operation, that MD4 sum, I expect this to be faster. So how much faster? Let's have a look. So in the old mode of netntl MV1, we just do the brute force functionality in hashcat. Should get an answer to this. Right, so you can see 132 mega hashes a second, which is really, really good. If we run it with my one, which is now, remember, skipping an entire operation. So in my mind, it should be faster. We get a factor of 10 slower. Now, this is quite interesting. So I was a bit taken away. I first assumed that it was my terrible coding, but ultimately all I had really done was just removed something from an existing module. I didn't think I would lose that much speed. So I got it explained to me, and it kind of makes sense why it's slower. And it all has to do with the way hashcat amplifies things. So the nice thing about hashcat is it has rules, and it applies those rules to sort of words, and that takes a single word and blows it up to lots and lots of words. So what happens in the background? Hashcat takes that word, it uploads it to the GPU. Onto the GPU, it loads all the rules, and it blows that word up into millions and millions of words, and then it hashes them all and sees which one match, right? If we compare that to my one, where we take the hash, we upload it to the GPU, we compare, and then we get the next hash, there's a lot more movement happening from disk to GPU. So that bus is acting as is throttling us effectively. Whereas with the original mode, you're doing a lot less data over the bus and a lot more work on the GPU. Therefore, you can get a lot faster. Right. So, interestingly enough, it turns out removing that operation in terms of hashcat makes it slower. But not all is lost. So Dominic carried on from here. He did some investigation, and that is what he's going to go through now. He's going to overcome this sort of throttling that doing it purely in hashcat ends us up with. Cool, Dominic.
Thanks, Michael. All right, so Michael has covered why we don't need the cleartext password. We just need to recover the NT hash, and he's looked at how we can use hashlists, like Have I Been Pwned, to crack things. We don't need word lists. That's great, but the problem he runs into is it's a little slow. So let's see if we can improve on that with looking a little bit more at the ass of things here. Okay, so picking up on the theory from where Michael left off, if the client is generating an NT response, what it does is it takes the password hash and it splits it into 3 keys. The first 2 keys are the first 7 and second 7 bytes respectively, but then there's only 2 bytes left in the password hash. So the third key isn't long enough, and it gets padded with 5 null bytes. These 3 keys are then used in 3 separate DES calculations to encrypt the same challenge. So the password hash is used as the key, or the part of the password hash. The challenge is used as the clear text, and then the ciphertext, or the result of that, is used to construct the NT response that Michael was talking about. Now, this is what happens if a legitimate client is engaging in an MS Chap operation. However, when we are cracking things, it's going to go in reverse. So what we've got is the challenge. Now, you'll remember the challenge is made up of the peer challenge, the authenticator challenge, and the username. So we can't rainbow table things here. And we've got the NT response. What we want to recover is the password hash. So that is broken up. The NT response is broken up into the 3 ciphertexts that we have. We know that the challenge is encrypted. What we need to recover is the key. Now, way back in 2003, it was pointed out that you can brute force these 2 bytes here. So if we have the ciphertext that we do on the right, and we have the challenge that we saw in the previous instance, we go through 65,535 iterations of DES at most. On average, it would be half that, and we get these two bytes. DES operations on modern computers are pretty efficient, so it doesn't take very long. Like I said, this was first discovered in 2003 by Joshua Wright. You'll see in the middle of his slide there, it says permits recovery of 2 bytes of the anti-hash. You'll also notice the Alexis Park sign on his podium there, which is kind of cool. Right, in 2012, Moxie Marlinspike and David Hulton's DEF CON talk pointed this out, but they pointed out another cryptanalysis. So after they had recovered those 2 bytes, they then iterated through DES's key space, which is 2 to the power 56 because it's 56 bits. So that's very big. And they would encrypt once and compare twice. So to recover the 2 keys, they wouldn't walk through DES key space twice. They just walk through once, but compare twice. So do the crypto result for each key, each iteration of the key. And if the result matches the ciphertext, then they know they've recovered either key 1 or key 2. This is not particularly different from how people have done things in the past. Things have just gotten faster and cheaper or more available. So this is a brief history of this work. In 1998, the EFF released Deep Crack. They were using ASICs, which are in effect custom chips, and it took around 227 hours to go through the full DES key space, but it cost $250,000, which is quite a lot. In 2006, the Copacabana team used FPGAs, which are cheaper, so it only cost $10,000, but it still took around 307 hours to go through the full DES key space. 2012's work from Moxie and David, they created Cloudcracker. I don't know how much it cost them. They were also using FPGAs, but it only took 23 hours to go through the full DES key space, and they made it freely available on the internet so that the rest of us could use it, which was pretty cool. The forum posts that Michael referenced earlier on 32 RTX 980s, hashcat would take around 48 hours at that time, and it would have cost you around $10,000 in 2016 for that. So we've now moved from FPGAs to GPUs, and then in 2020, using 16 GTX 3080s, cost you around $11,000. We're achieving similar speed to what they were getting in 2012 with an FPGA. So the one thing these all have in common is certainly expensive. You know, if I've paid for a $2,000 laptop or computer, to also shell out all of that for GPU is quite expensive, but it also just takes a long time. We want to see if we can do this a bit faster. So instead of coming up with a new cryptanalysis against DES or new hardware which would improve things, we looked to try and escape this constraint. So MSChap doesn't protect its ass. We can brute force these last 2 bytes. That gives us the last 2 bytes of the password hash. And Michael showed us that we can crack using hash lists rather than word lists. So if we combine those two, let's just reduce the number of hashes we need to crack by only looking for hashes that match the last 2 bytes. Now, this isn't new. Hashcat does this already. For the existing 5,500 hashcat modes, it will do an early discard of empty hashes that get generated that don't match the last 2 bytes. However, I'm taking a different approach here. I'm upfront limiting the number of empty hashes that we're going to send to hashcat to get cracked in the first place. Well, this was my first POC anyway. I just grepped a hash list for anything ending in those 2 bytes. And the initial speed was interesting enough to continue. So these are terrible measurements taken very unscientifically, but what it showed was that on a small hash list of about 2.6 million hashes, hashcat was taking nearly 9 seconds. Assless Chaps, as I was calling it, is taking less than a second. On a big hash list, the Have I Been Pwned hash list with 613 million hashes, we were getting somewhere between 3 and 1 minute on hashcat and 40 to 50 seconds with Assless. So not amazing, but interesting enough from a POC perspective to say, let's dig into this a little more. So I decided to bravely venture forth into the unknown. And that led me to the dark path of performance optimization. There were a couple of things I tried to speed things up. I'm going to take you through them, tell you what worked well and what worked not so well. So the first unimaginative optimization was I used ripgrep, which is a faster grep written in Rust and some other performance optimizations. And then I also streamed the output into my now POC Python code rather than waiting for the full operation to end before I started any of the NT cracking. That gave me a pretty decent speed up. Next thing I did is I looked to try and optimize the 2-byte brute force, so brute forcing the ass. And what I realized is not all asses are created equal. Some asses show up more often than other asses. When I looked at a list of unique NT hashes, I noticed that some 2-bytes showed up significantly more than other sets of 2 bytes. The other thing I noticed is that on an ununique set of hashes, something like password 1 is going to be at the top of that list, and maybe a password from a password manager would be at the bottom of that list. So even if the 2 bytes at the end of password 1 don't show up within a des operation very often, they do show up in a password list very often. So we want to include that as well. So I generated a frequency, sorted frequency list of the most common 2 bytes using an ununique set of passwords as well as 2 bytes. That's published with the Assless Chaps repository. I'm going to show you a bit later. So that gave me quite a decent speed up. For common passwords, it was going through hundreds of rounds of des iterations rather than tens of thousands of rounds of des iterations. Then I started looking at file tricks. How could I make ripgrep go faster by reducing the file size or improving where I'm seeking from in the file? I tried a couple of things here, but in the end, what I realized is I was just badly re-implementing what databases already do quite intelligently. So then I switched to databases. First, I tried MariaDB. It was slower than the original grep. Then I tried SQLite. It was even slower than that. Scratching my head, I wondered why, even in cases like 2.6 million hashes, databases were slow. They're meant to handle more than this. Until a developer friend of mine pointed out that I was being a bonehead and I need to actually index the table. So once I enabled database indexing, things sped up dramatically. Database indexes give you balanced trees and log n big O performance, which is much faster. So that was probably the biggest speed increase, and it's really the BuzzFeed one simple trick to crack your hashes faster of this whole thing. After that, I rewrote my Python POC in Rust. Rust being a compiled language is faster, and Rust also lets you get things pretty efficient. I then fiddled a lot with threading models. So first I wanted to see if I could use different threads to crack the returned NT hashes from the database lookup. I tried numerous different models there. At most, they came out the same speed as doing that in a single thread. At worst, they made things longer. Then I looked at threading the 2-byte brute force, and that actually worked quite well. And it gave me, on average, better performance than the optimized 2-byte lookup list. So I kept that in there. All in all, I got some pretty decent speed improvements into the order of milliseconds. I'll show you that in a moment, but it's worth looking at some of the theory behind this here. So because the red line, which is assless, and the blue line, which is brute forcing des, are different operations, I wanted to understand, like, at what is this always more efficient, or does it change based on some level of hashes? Now, if we were just doing a database lookup, it would always end up more efficient. But because we're doing a database lookup and then we have to crack that hashes, or we have to iterate through all of the hashes returned from that database lookup, we don't get a smooth straight line. These are 2 logarithmic scales, so that's why it's shown as a straight line. The 2 axes, on the y-axis, we've got number of operations. On the x-axis, we've got number of hashes. So at a simplistic level, if the x-axis is on 1 million hashes, that would mean Assless has got a database with 1 million hashes in it, and it would mean a des brute force had produced 1 million hashes through a certain number of des operations, the square root of the number of hashes, really. And the point at which these two cross over, assuming all computer operations are made equal, is 4.3 billion hashes. So that means worst case performance for Assless at 4.3 billion hashes, the des brute force is going to be better. Average case performance is 17 billion hashes. Now, most of our word lists are less than that, so that still neatly fits into what we're looking for. And if we switch over to the actual timings, you'll see, and I'll explain these in a bit more detail, but the average and median times are so fast that we can use lots of databases here. It doesn't really matter too much. So what this table is showing is, on the left, I used 3 different hashes. Hash 3 doesn't exist in those databases to simulate worst case performance. And then I used 3 different lists of hashes. The small private list was 2.6 million hashes. RockU is 13.8 million hashes. and Have I Been Pwned is 613 million hashes. And what you can see, other than the outlier in the bottom right of 63 milliseconds, it was generally between 11 and 19 milliseconds, which is pretty fast. The 63 milliseconds is worst case performance against Have I Been Pwned when it can't find the hash. Now, if you think back to Rip Van Winkle, the best case performance we had was Cloudcracker or 32 GPUs, still taking 23 hours to go through the full key space. Getting things down to an order of milliseconds is pretty significant. Importantly, though, this will only return a hash that you already have in a database. It's not guaranteed to return a hash. So you've got a likelihood advantage because the hashes that a DES brute force will generate, some of those aren't necessarily going to be human readable, but you lose out in that you're not guaranteed to get a response. So if you've got databases of 1 billion or more, and it's not returning from those, then maybe it makes sense to switch over to DES key space brute. But for most information security auditors or pen testers that need to rapidly check if a password is in a word list, this is going to work for you. And if you're running rogue AP attacks where you want to do something like auto crack and add to make sure that a client authenticates to your evil AP, then this works out pretty well for you as well. So this is available right now. You can get it on github.com/sensepost/assless-chaps. I want to give you a quick demo of what that looks like. Switch over to the terminal here. And it's really simple. If you take the binary Assless Chaps, you pass it the challenge and then the response. That's what those two hex numbers are. The first is the challenge. The second is the NT response. And then you point it at a SQLite database that has the NT hashes in them. I'll go into what those look like in a moment. You run it, and it returns pretty quickly. And if you look at the output, what you'll notice is that the 2 bytes were brute forced in 22,636 DES iterations. But we're talking sub-second response times here. So when I say DES is very efficient on modern CPUs, this is what I mean. I'm not using a GPU here. As a matter of fact, our GPUs are maxed out doing this recording, so this is done on CPU. And it's not a particularly fancy laptop. It's 2016 MacBook Pro that we're doing it on. So this becomes very portable. Then of the hashes returned from the database, we found it at the first hash, rather conveniently. So that went a little faster. But even if we had to go through 22,000 hashes like we did, or DES operations like we did in that first line, it really doesn't take very long. So that's quite simply how to run Assless. It's a very simple tool, very simple command to run it. Like I said, you can get it on GitHub right now. Pull requests always welcome. Okay, the next thing we ran into is Michael had been using the Have I Been Pwned hash list, which is great. It's a large hash list. It's got passwords that we know users actually use. However, the kinds of passwords that are in Have I Been Pwned from websites that don't enforce the same password complexity that Active Directory domains do. And the kinds of places that tend to use PEEP are places that use Active Directory and Microsoft's defaults. So we wanted hash lists that contain passwords that are more likely to show up in Windows Active Directory domains. And Have I Been Pwned isn't that. What is very good at producing those kind of passwords is hashcat with word lists and their rules. So many of you be familiar with this, but just to explain it for those who aren't, if you have some very simple words in a word list like password or the company name, and you've got some very simple rules like adding numbers, changing the case, and adding dates, it'll generate example passwords like on the right. So instead of password all lowercase, you're going to uppercase the P because that's what people commonly do, and you're going to add a number on the end, or the name of the company, Acme Corp 1, etc. So it's quite useful to be able to generate hash lists for a custom engagement. If you're going to do a project, you can take 2 hours to generate a massive hash list using some word lists where you've injected the company name, and then you can run rogue AP attacks, benefit from auto crack and add, and other rapid hash cracking speeds, even if it's just to show that the hash doesn't show up in a common word list. So the way you can do this is Michael made some modifications to hashcat that will spit out the empty hash. Now, Assless is using a SQLite database, but we don't just import the empty hash as a string. What we do is we break it into 3 parts. The last 2 bytes go first, and that's what we put the index on. And then the first 7 bytes and the second 7 bytes. We chunk it up. So I'm going to show you our modified hashcat here, what that looks like. This is available in the GitHub repository. Let's put this at the top, paste that in there. So I'm running the modified hashcat. All we've modified is the 1000 module. We're pointing at an impossible hash, or a hash that won't crack, because we want to fully go through the word list and the rules. I've got a very simple word list just for demonstration purposes, and I'm using hashcat's built-in best64 rule. And what you'll notice is it'll output it in the CSV format that we need to consume for Assless. And Assless Chaps has got a Python script called make SQLiteDB in the repository that will consume these and turn it into a SQLite database and generate the index for you. Doing that will increase the size or the disk space requirements by about 63%. So if you take something like Have I Been Pwned, which has got, it's 21 gigabytes uncompressed. When you import that into SQLite and then add a database index on there, it turns into 33 gigs. That 63% is consistent across RockU2, so I'm guessing it will be consistent across other databases too when you're importing that in there. So now we have an ability to generate our own hash lists, and we've got an ability to look them up very, very efficiently. So that brings us to the end of our talk. Before I hand over to Michael to do a little bit of a wrap up, what we've got at this point is we know that MS-Chap, we can use the anti-hash rather than the cleartext password. We know that we can crack against hash lists rather than word lists. We've got a very efficient way to look up the hash once we know about what the ass of that password is. And we've got a way that we can generate hash lists. So on that note, I'm going to hand back to my colleague, Michael.
Cool. Thank you. Let's wrap this up. Right. So the main thing, why are we doing this? We want to be able to recover empty hashes quickly. Even though there's a space trade-off, the speed we get from this is really good, and we can use it in further attacks, such as passing the hash to get onto Wi-Fi, passing the hash to sort of SMB authentication, go onto VPNs, etc., such as PPTP or SSTP. And then also the one that originally led me down this road was reusing those hashes to get people via rogue APs, to return a valid success at the end of the day. So in summary, what have we learned during this talk? MS-Chap v2 uses the NT hash, not the cleartext password, which makes sense because that's how Microsoft stores these hashes. You can use NT hash lists, including the uncracked ones, so it means we don't have to go through the extra effort of cracking those things. We've sort of introduced two new hashcat modes, 27,000, 27,100 for NTLM v1, and as a bonus NTLM v2. MS-Chap v2 exposes its arse, easy brute force of the last 2 bytes, which allows us to reduce the hash list that we're going to crack against. Index DB lookups cost less than DES brute forces, provided you are less than 17 billion hashes, etc. So there's some people I would like to thank. So first, I would like to thank the hackathon team that forced me to finally make the module, and then with their help as well, eventually submitting it as a pull request to Hashcat. Once they're in Hashcat, I'd like to thank Atom and Chicken Man. Both of them provided a lot of input to make it a better module for Hashcat as a whole, so that you didn't have to do all sorts of... While I was trying to get away from annoyances, I also introduced some annoyances, so they got me to get rid of those, which is really cool. I'd like to thank Joshua Wright for Asleep and all the work around that. Moxie and David for Cloudcrack, as well as all the work around that. And then an additional mention for Chicken Man. At DEF CON last year, he did a talk on something called hash shucking, which is essentially what I've just explained with NTLM v1 and v2, except he's sort of more generalized it to a bunch of other hashes as well. So if this sort of technique intrigues you, you should definitely go watch that. And then finally, where you can get the code, once again, is sensepost Assless Chaps. For the hashcat code from my side, that should hopefully be in the main hashcat by this point. So enjoy that. And the end. Thank you very much.
Thanks for joining us for our talk. Have an awesome con.